For centuries, the boundaries of the known universe were defined by the glass lenses of ground-based telescopes. We were limited to the narrow slice of the electromagnetic spectrum that our eyes could perceive and our atmosphere would allow through. Launching observatories into orbit changed our perspective by stripping away atmospheric distortion. High above the clouds, telescopes like Hubble could finally capture the faint, ancient light of galaxies that had been traveling for billions of years. The next technological leap required us to look beyond visible light entirely. By using infrared sensors, the James Webb Space Telescope can peer through interstellar dust to observe the earliest structural formations in the first few 100 million years of cosmic history. This works because light has a speed limit. When visualized as a series of concentric shells, we see photons from the closest shells arrive almost instantly, while light from older, distant shells has been traveling for nearly the entire age of the universe. But as we push our gaze further back, toward the very beginning, we hit a definitive limit. Approximately 380,000 years after the Big Bang, the trail of light simply ends, leaving our most powerful instruments staring into an impenetrable wall of black. This barrier exists because we have reached an era that produced absolutely no visible light. It is a period that forces us to redefine what it means to observe the universe. This period is known as the Cosmic Dark Ages. During these hundreds of millions of years, the superheated plasma of the early universe cooled down enough for protons and electrons to bond, creating a vast, uniform mist of neutral hydrogen gas. Because the first stars had yet to ignite, there were no sources of radiation to illuminate this gas. The initial glow of the Big Bang cooled and shifted out of the visible spectrum, and the lights of the universe were effectively extinguished. This creates a fundamental disconnect with our current technology. Human sensors are designed to catch photons. If an era produces no light for our mirrors to reflect, that entire epoch appears as an unreadable void. Without a new method of detection, we have no way to track how the structural foundations of the cosmos were built. We are left with a massive billion-year gap in the story of how our universe came to be. In this total blackness, a hidden component of mass was already dictating the shape of the cosmos. Astronomers call it dark matter, and though it is invisible, it was the primary builder of the early universe. Dark matter is unique because it only interacts with gravity. It cannot absorb or emit light, but its immense gravitational pull allowed it to collapse and clump together long before ordinary matter could. Gravity pulled the early universe into an interconnected scaffolding, a 3D web of filaments meeting at dense nodes. This web trapped invisible hydrogen gas, siphoning it into these hubs, pooling into massive clouds that eventually became the first galaxies. This was a period of quiet, massive construction. The universe was assembling its most important structures in total silence, hidden from every optical telescope we have ever built. Mapping this invisible hydrogen requires looking past the visible spectrum to a specific anomaly in the hydrogen atom itself. Every hydrogen atom has a proton and an electron, both possessing a property called spin. Usually they spin in the same direction, creating a higher energy state. Occasionally, an electron spontaneously flips its spin to the opposite direction, releasing a tiny specific parcel of energy. This exact quantum transition emits a radio wave precisely 21 centimeters long. This wavelength is completely unaffected by the darkness, traveling through the gas clouds without being absorbed. While this flip is incredibly rare for a single atom, the early universe contained such a staggering volume of hydrogen that these whispers combined into a constant, measurable radio broadcast we can detect today. To capture this ancient 21-centimeter signal, astronomers must move away from the light pollution of cities and the interference of satellites. They head to the most desolate places on Earth to build vast arrays of metal antennas designed to listen rather than look. As those radio waves traveled toward us over the last 13 billion years, the expansion of the universe caused them to stretch. By the time they reach these antennas in the outback, those 21-centimeter signals have been pulled into meter-long radio waves. These waves allow us to witness the end of the Dark Ages. As the first stars flared to life, their radiation heated the nearby hydrogen gas. Because the 21 centimeter signal is sensitive to the temperature of the atoms, this heat left a distinct imprint on the radio waves, marking the exact moment the first light appeared. This radiation triggered the epoch of reionization. The fierce energy from these new stars stripped the electrons away from the neutral hydrogen, carving out massive bubbles of ionized gas that eventually merged to clear the cosmic fog and end the Dark Ages. The radio universe reveals that the Dark Ages were a time of intense industry. Behind the blackness, invisible forces were weaving the structure of the cosmos, waiting for humanity to develop the right kind of eyes to see them.